My name is Sarah Parker, and we are going to begin our group project presentation for computer algorithms. Our group consists of myself, Melissa Stan, and Cecily Holland. We are tackling the issue of patients waiting in the emergency department for long periods of time while waiting for an ICU bed. And we created a novel scheduling algorithm using machine learning assisted scheduling. So the challenge is that ICU patients come into the ER, they are determined to need an ICU bed, and then they wait. And it's a traditional first come, first serve priority, or first come, first serve queue. We are changing that to a priority queue based off of multi-factor risk assessment using a machine learning based length of stay prediction, and if needed, an aging mechanism to reassign priority. Go to the next slide. And so for the queue, we are assigning patients a priority level, and this is based on multiple factors such as the severity of their diagnosis, the stability of their vital signs, their age, and their comorbidities. We created a base length of stay just based off of their diagnoses, and then adjusted this as needed for comorbidities. And then we have an aging mechanism for patients that are waiting excessively long periods that are considered lower priority in the lower moderate category, so that their priority level increases closer to that critical level, to make sure that they're not waiting excessively while higher priority patients get beds faster. We can go to the next slide. And this is just kind of the queue management cycle. We pull a patient that needs to be admitted. They are assigned a risk category based off of our algorithm. They have an estimated length of stay. They are added to that queue. And then when an event happens, then their priority is updated in the queue. The data structure is a queue data structure, and it is a min-heat priority queue because we are pulling those patients with a level 1 priority because they are higher urgency, and this runs in an O log N operation. In our data class, the patient's clinical data is saved in the queue as long as how long they've been waiting in the queue and their current and their original risk categories.
Okay, so moving into the ICU length of stay forecasting, we use survival modeling for this because ICU beds are very high cost. They're about $3,000 per day, and they're a limited resource across regions and hospital systems. So the longer the wait from the emergency department to the ICU, the higher increased mortality risk for that patient. And so prolonged waits are also increasing post-admission length of stay, and hospitals need patient-specific length of stay forecasts to be able to plan bed turnover, prioritize transfers, staff appropriately, and support surge time scheduling algorithms can help mitigate that. We use survival models in this case because the ICU length of stay is not a normal regression problem. It's very right skewed distribution with very heavy tails, and the observations are censored, meaning that some patients are still in the hospital that are in the data set, and not all of it's a historical data set. So we had to have the model account for those additional parameters and adjustments. And the length of stay is fundamentally a time to event outcome. And our solution for this was to use the survival models, which are able to handle the censoring, like I said, produce survival curves, and give those median length of stay predictions working with a small data set. The models we used to evaluate this were the Cox proportional hazards, Cox-PH, and log normal accelerated failure time, or AFT. For Cox proportional, we wanted to look at it because it's semi-parametric. It estimates hazards of discharge. It's very interpretable, and it's good for early horizon calibration. So this worked really well with our data set. And then for AFT, it's fully parametric, so we were able to see the difference between the two. It models the length of stay in log time, and it directly yields those median length of stay results, as well as handling the heavy-tailed length of stay better. So some of the evaluation metrics that we used when looking at these were the C index as well as the Breyer score. For C index, that ranking accuracy from 0.5, which sort of means that the estimation is random, to 1.0, which is that the estimation is perfect or exactly accurate. and that Breyer score, looking at the probability calibration at specific times. Lower is better, and for that one, and the horizons we evaluated were 24, 48, and 120 hours. So these are some of the results we got using those models. You can see that the C index is around 5.2, which means the model performs slightly above random. And this is expected given how small our synthetic data set is. But the Cox performs better at the early horizons, the 24 and 48 hours, where the AFT model performs better at 120 hours. But despite the noise, both models successfully produce usable median length of stay forecasts. And because the scheduler doesn't require perfect accuracy, it only needs relative ordering. And these predictions are sufficient for queue prioritization. We then exported these into 2 files. You can see the length of stay prediction for scheduler on the left is a minimal format. It was more for debugging and model evaluation, but we left it in for curious people. But it contains the true length of stay versus the predicted length of stay of our historical data set. And then the scheduler input length of stay merges the predictions back into the active Cynthia cohort of patients who are still in the hospital utilizing bed resources. So this scheduler input length of stay is the full integration data set, and this file feeds directly into the scheduling model.
Okay, so I'll be talking about the scheduling for the ICU bed allocation. So we actually created a formula to assess the priority. To do that, we're going to need severity plus the risk minus the LOS plus the aging. Now for the severity, we use a triage category where 1 is being the baseline, and both risk and LOS comes from Cecily's forecasting, LOS or LOS forecasting. And aging part, now we added this in case if there's extremely long waits, and so for the aging process, we just made sure that it's actually really optional and we don't really need it unless it's a really long wait times for all the patients. So all the patients will then be ordered by their effective priority. Okay, for the simulations, there's a couple of conditions that we need to instill. Let's go ahead into the next slide. Okay, so then for the surge simulation, we have to make sure that the ICU operates at 95% capacity. Now, having that high capacity is because we're trying to, again, make it like a surge situation where there's a bunch of patients coming in through the door, but we are also operating where there's patients already on the bed. Now, speaking of beds, we're using 27 beds. Now, this number comes from Park Ridge Hospital number of beds. Since it's the closest hospital to us, we thought it would be great if we can try to mimic their ICU. And so we're going to start off with having 25 patients already in beds, and that only leaves 2 beds available. And so that allows us, like, if incoming patients, they have to wait to actually get a bed. Now, for the goal of this, again, is to make sure that this mimics the real world of ICU crowding patterns. Okay, so for the patient arrivals, we have to add some unpredictability to it. To do this, we're going to use the Poisson process, and so we're going to set that equal to the arrival rate per day, and so that means about, we set it to 120 patients coming through in the next 18 to 36 hours, and by setting to such a high number, we're expecting to have more of a congested area and longer wait times, but having a lower number will just yield to nearly 0 waiting times for those patients. Okay, so for this event, there's going to be 2 types. There's going to be the patient's arrival and then patient's discharge. Patient's arrival, what's going to happen is patient comes in. They shouldn't get a bed immediately unless if they have the highest priority. But what happens is they get a priority and they sit in the queue. And then patients who are then getting discharged, what happens there is that a bed becomes available. Then we're going to take a look at the queue. We're going to take the highest priority, take that patient, and then we're going to go ahead and give them a bed. And then we're assigning the beds to their priorities. Now, and then we're going to schedule their future discharge. Now, again, we're making sure that we're recalculating the effective priority to make sure that someone who has a lower priority, they're eventually going to get executed and they're getting reformulated. But in case if they don't, then we can apply aging to that aspect. And so that way, patients who come in, they don't just jump the line. They are waiting in the queue. So we're not following the FIFO model. Alrighty, so for the results, we're gonna go over what happened in our simulation model. So for the average waiting time, it came out to be 16 minutes, which isn't really reasonable. However, that is just one of our limitations to our model here. But the longest time was actually 3 hours, which is, I say it's pretty good. But for the IC utilization, it came out to be 88.5%, which means that we are using the IC room, so that's good. And again, we were trying to mimic surge conditions here. And for the initial beds, we're going to only get 25 beds are actually occupied by patients, but only having 2 available beds. So first 2 patients come in, they can get a bed immediately, but after that, some patients are going to have to wait. And so we have set here the Python time to be 120 arrivals per day. And we found that the actual wait for low risk is 0.87, so a little less than an hour, which makes sense because they're real low risk. Those patients are not in critical need to be getting a bed. But medium and high risk are going to be stuck at 0.21 to 0.24 hours, so a little less than half an hour.
Okay, and I'm just going to conclude this presentation with our limitations. So we used a synthetic data set rather than real data. We selected 66 patients, which is a relatively small data set to work with. But if we used real patient data, we would have access to more clinical indicators and historical data for ICU admissions and wait times. We ran our simulation off a single surge scenario, but in the future you could run this off of multiple different fixed arrival rates and occupancy, and just to test it further to see what the actual wait times would be. For us, the only limitation was bed availability, but in the real world, ICU bottlenecking can happen because of staffing. If there's not enough staff, then the full amount of beds may not be able to be utilized. For future use, you could run the Monte Carlo simulation across a wide range of arrival rates just to see what the times end up being, just to give it some more robustness. We created our own risk scores based off of actual acuity scores, but you could use real triage acuity scores. And then you could also use multiple hospitals to distribute the surge load, such as Park Ridge has multiple ICUs in Hamilton County. So if one becomes over at capacity, people could be transferred to a different facility. So this was our novel algorithm to tackle long wait times in the ER for ICU beds. We feel like this has some great real world implications and could really help ICUs become more efficient at discharging patients and then admitting patients for more effective bed use in the ICU. Thank you.
Thank you.
Thank you.